Okay, so the goal is to so the goal is to show how to construct hyperkählers of dimension 6 and 10, which are not deformations of Beauville examples, but actually so but actually these they come out of moduli of semi-stable sheaves, and actually these moduli of semi-stable sheaves on symplectic surfaces, I'll be more specific, they give sort of explicit constructions of hyperkählers, most of them deformations of Beauville examples. So I think I'll spend most of the time, I will explain this general construction. I won't have a lot of time to explain the details of these particular ones, but I think it's more appropriate for people who are not familiar with these constructions to explain these. And maybe one can even go back to Claire's first class. So Claire started by talking about compact complex tori and abelian varieties. And so maybe we can have somehow an analogy. Here, so we can have, let's say, abelian varieties. Okay, and I think historically the first instance in which these appeared was you have a smooth projective curve, I mean a Riemann surface, and C, and the construction somehow by, I guess, Abel and Jacobi of pic naught of C, okay, or the Jacobian of C. Okay, and here, if we look at, say, projective hyperkählers, what we have is we start with X, smooth projective symplectic surface. So that means that X is either a K3, a projective K3, or an abelian surface. And you consider a certain, I'll explain the notation later, a moduli space of semi-stable sheaves on X, okay? And you can even notice that here, So if we vary C, pick not of C is not this thing not locally complete if the dimension, unless the dimension of pick not is less or equal than 3, and similarly here, if you vary x, this is this mv of x is not locally complete unless the dimension of this mv is 2. So it's somewhat very similar picture. Okay, so I want to explain something about what is known about these moduli. So x is always is either projective, polarized K3, or I don't know if abelian variety means it's polarized, but anyway, an abelian surface. Okay, so that's a smooth projective symplectic surface. Okay, and we want to consider an H is a polarization. So we choose one. We need one to define semi-stability. Okay, and so we want to study H Gieseker Mariama. Okay, so I won't say what this means for those who are not familiar with it, but anyway, it's a condition on the sheaves which depends on the polarization, but it's sort of because if you take so you want to consider say locally free sheaves modulo isomorphism. So if you don't if the rank is at least 2, if you don't put some condition, you'll get a non-Hausdorff, and it's not you don't get a bounded family and so on. So this is a condition that allows you to get a bounded family, and so you get a projective modular space. I'll recall this later. Okay, and so the main principle, I think here, I mean a posteriori, is that if we look at these moduli spaces up to deformation, moduli spaces depend only on the numerical character of sheaves. I mean, say the churn. Okay, so this is, and so let me give you right away an instance of this principle. First instance. Let's look at locally. This is exactly what Claire just mentioned. So we have, although here it's useful not to consider only torsion-free sheaves, we want to consider pure sheaves. F, of course, these are always coherent sheaves. So pure means that no proper subsheaf of dimension such that dimension of support of E is strictly small. Okay? So we'll see at the end some instance of this. Okay? In particular, torsion-free sheaves. Okay? So let's say we have such a sheaf on X, and okay, assume that it's H stable. Assume that F is H stable. Then the moduli space, okay, so maybe I should introduce. Then, let's say, for the moment, we'll just say, now I'm a bit vague, then I'll be more precise. E pure sheaves on X. Now, this is not something we will really consider. For the moment, it's okay, because this will be a non-separated, whatever, algebraic space, something horrible, okay? But in a neighborhood of a stable sheaf, it's fine, okay? So for the moment, I don't need to introduce. So not nice, but okay near such an F. Okay, so that's, I want to avoid introducing heavy notation for the moment being. Okay, and assume F is stable, then M is smooth at F. This is the isomorphism class of F. I'll put the brackets. And dimension at that point the point is that this is the Zariski tangent space of M at F. Okay? And why is this? Well, this is because you want to consider so in a neighborhood of F, M is the same thing as the deformation space of F, and the obstruction. You mean, so yeah, the Giesecke-Mariuyama is defined, stability is defined using the Hilbert polynomial with respect to H. Yeah, so if it's H slope stable, it's H Giesecke-Mariuyama stable. And if it's H Giesecke-Mariuyama semi-stable, it's H slope semi-stable. Obstruction space is equal to the, well, it's contained, I guess. I'm always these, I never understood deformation theory, but anyway. So this is the trace map. There's a trace map. But this is if I didn't screw up things, you can look at the, if you look at the transpose map, this is by Serre duality. Let's say now any smooth projective surface for the moment. This is a general fact. So if we look at the dual, we're going from H now of kx to of f tensor kx. Okay, so now if kx is trivial, this map is easy. While the trace is sort of slightly mysterious, this map is you have a section and you map it through the identity of f tensor that section. So this is easy to describe. That's why I went to the dual. But now, if k is trivial, this is the map going from O. If k is trivial, these are just endomorphisms of f. But now, if it's, so what we're mapping, the image here are just the constant scalar endomorphism. But since f is h-stable, there are no other endomorphisms. So I repeat this. If k of x is trivial, this space here is just a space of endomorphism of f. Since f is stable, there are, any endomorphism is just a scalar multiplication by something. And so this map is an isomorphism. And so the co-curl is 0 and the dual is 0. Okay, so that's why. So you see, we have a mini instance of this. The local structure up to deformation, I mean, in the analytic topology for stable sheaf only depends on the dimension, I mean, on something which comes from the Chern character of f. Okay? Okay, and notice that, okay? So of course, notice that if we have a surface with many sections, where the canonical, say, is ample, there can very well be homomorphism from f to f tensor k, which are not multiplication by a section of k. And then there will be singular points of the corresponding moduli space. So this is really specific. Of course, if kx has no sections, it's even that, okay? And then another, I'm sorry, this is a theorem. I mean, this is, the point is to show that the abstraction space is in here. This is a theorem. I'll try to give references. I certainly will forget some okay? But then there is an important fact is so maybe I can put my name here also, at least to check some things, okay? So this again, any x as above, okay? For the moment. And given a section of the canonical, one gets a symplectic, regular symplectic form on, let me be vague, I mean it's, so I'll put S, I'll come to you, Claire. So these are the stable, H-stable things, yes? Yeah, thanks, Claire. Yeah, so we get a regular 2 form, yes, thanks. And it will be, yes, certainly. Since I insisted that X is any. Okay? So we get a regular 2 form, and it's defined like that. So let's give it a name. I don't know. Despite Daniel, I'll call this omega sigma. And, okay, so what do we have? We want to So I want to define it point by point, and so alpha and beta are in here, right? Because I said that this is the Zariski tangent space, so alpha and beta are in here, okay? And so where do I map it? I integrate over x. So alpha kappa beta, this is the Yoneda pairing, so I get into x2 of ff. It's easier to think that f is locally free than alpha and beta elements of the Dolbeau group H01 of f. So locally, these are just f. So it's in H01 of endomorphism of f. So locally, these are just square matrices with entries 0,1 forms. You have two of them. You take the product of matrices, and then you just take the trace. So you get a 0,2 form, which is closed. And that's this trace. And then you wedge with your sigma. So you get so this is a 0,2 form. This is a 2,0 form. So you have you're integrating a 2,2 form. So this is some number. Okay? And now, so in general, this can be degenerate even everywhere. For example, the moduli space can have odd dimension in general, so it cannot. But Serre duality gives you that if x is symplectic, omega sigma, and sigma is different from 0, omega sigma is symplectic. I mean, it's always, you have to check that it's closed, right? So, I mean, there is something to be proved. Okay? So it's a closed.
With this formal definition of the two form, it's not so easy to show that it's closed. It's better to make use universal construction.
Yeah, but that's, at least that's what that's what I did. I identified it with that. But how do you, but if you have the universal, okay, then checking that it's, I mean, this is better if you want in general to see where it is degenerate. I mean, this is better. I guess for symplectic surfaces, you can see that it is symplectic without going through the identification. I guess you just have to check it on the Hilbert scheme. That's what you're saying. I mean, you want to, I mean, how do you know that this is symplectic? So this gives you, so on a symplectic surface, this definition gives you that it's symplectic, but then to see that it's closed, you have to go through some other identification. Yes, it's not clear that it's closed this way. Yeah, but it is. Okay, so, okay, so now from now on, we will only have this kind of surface, okay? So why? Because we've just seen that with this choice of surface, we get pieces. I mean, this open piece of the moduli space of this huge infinite dimensional moduli space is symplectic, and so the idea is to use this to produce hyper-Kähler varieties. Okay? But so now I have to introduce some notation in order to be more precise. Okay? So this, so maybe I'll use this blackboard. Okay, so we need to introduce some notation, and okay, so if we want to get a projective moduli space by a theorem, I mean a well-known theorem of Giesecke and Maruyama, we have to fix rank C1 and C2 of the sheaves, of the semi-stable sheaves, and then we cannot take isomorphism relation on strictly semi-stable sheaves. We have to take something which is called S-equivalence. But anyway, on stable sheaves, this is just isomorphism. Okay? So, but it's convenient to introduce, okay? So we want to indicize moduli spaces. I mean, components of this huge M. Okay? So, I always have F like that. It's not necessarily stable, but I have a X now is a symplectic surface, and we have a coherent sheaf on X. Okay? And so view of this is the Mukai vector of. So this is all of the early work on this is due to Mukai, and so this is essentially the Chern character of F, only that we multiply by the square root of tot of X. Okay, so this is Eta is the fundamental class. Okay, and where do we want this to live? Okay, so this, of course, is in the even cohomology ring of X. This is we don't care of the odd cohomology if X is an abelian surface. Okay, and we also want to define the Mukai bilinear symmetric form on this object here. And so what we do is we have two cohomology classes. We map it to okay, so the dual of alpha so these are the components in H0, H2, and so the dual is simply okay. So why do we define this bilinear symmetric form? I'll tell you right away. The notation I'll use is something like okay, and so what is the point of defining this thing? Is that Hirzebruch-Riemann-Roch gives you that if you have two sheaves on X, this, which by definition is, let me write it the other way around. So, this is equal to, there's a minus sign, right? There's a minus. So this we denote. That's why we had the square root of Todd. So when you multiply, you get 2 of these, you get Todd of x, and that's Hilsebrück-Riemann-Roch gives you that. And that the dual here is because this comes with a dual. No, you're right. No, you're right. It must be, yes. No, it's that. So, because if you put it this way, here you would not get a minus sign. Yeah. Yes. So this is a minus sign. Okay.
What's the signification of H or?
Hilsebrück-Riemann-Roch. Yeah. Okay. So now what follows? So to thus, if f is stable, so dimension of we get that the dimension in f of m is 2 So, I mean, that explains why we have a minus sign here. Of course, one could do. So what happens is that we get dimension 0 if v of f squared is minus 2, and as it increases, we get bigger and bigger dimension. Otherwise, it would be the other way around. Okay? So that's the reason. Okay? Okay, so now we can indicize, finally, projective moduli spaces. So, okay, then we let, maybe we drop the h if it's not necessary. So we take f, h, semi-stable, such that the Mukai vector of f is equal to this given Mukai vector. Okay? And now this is a highly non-trivial theorem. This is, modulo what? Modulo S equivalence. So, on the open subset of stable sheaves, S equivalence is isomorphism. On properly semi-stable sheaves, it's a weaker notion. Okay? And now, this is this is MV is projective. This is a general result. Only here I want to indicize things for symplectic surfaces. This is valid for any smooth projective surface. Then Simpson generalized it to everything. Okay? And what we saw is smooth, this is smooth, symplectic of dimension, as we said, 2 plus v squared. This is what we have seen so far. Okay? So let me give some examples. And now I'll erase this left-hand side, otherwise there will be no... Yes, let's give some example. So I want to give... So one should always start with trivial examples, right? Yes. So, well, not so trivial. I mean, say x is a K3, and V is 1, 0, 1 minus n. So rank 1 sheaves, C1 is 0, and there is some, well, if you think here is a Brook-Riemann rock, the Euler characteristic is R plus S for K3s. So the Euler characteristic is 2 minus n. The sheaves has to be the ideal of a zero-dimensional scheme, and that means that the zero-dimensional scheme has length n. Of course, here H has no importance. So we're getting back the Beauville example. And see, I mean, the dimension checks. I mean, one has to get used to. So when you compute the square, we multiply 1 times 1 minus n. We get 1 minus n, and we get it 2 times. But then we have to change sign. What's that minus? So we get 2n minus 2. And for the dimension, we add 2, so we get 2n. And here, instead, we get so, of course, this is not a hyper-Kähler. What happens is that there is a specific Beauville-Bogomolov factor, which is a generalized Kummer. Okay? 1 Beauville-Bogomolov factor is a generalized Kummer. Say it again? Yeah, so you have a Natal cover from the generalized Kummer times x to this. And so that's the generalized Kummer is a Beauville-Bogomolov factor. This is wrong?
It's not an equality. I mean, there is this product, it's an Hyperkaehler of them.
No?
Because on the left, you have the Hilbert spin.
No, you have the moduli space. You take something like that. What are the deformations? You can deform O by putting an element of pick knot. This is in the moduli space. I mean, this has dimension 2n plus 2 according to that formula. If you look at V squared, this is 2n. Yeah. I mean, you can... Okay, now let's get to some geometrically more appealing examples. I'm not doing them. I'm doing them for, well, because they're nice examples. Of course, I'll be running out of time. But so let's take a K3 surface of genus G. Okay, and let's take, of course, H is C1. And V is 2H2. Okay, so v squared. So we have h squared, which is 2g minus 2. And then we have 4 plus 4, 8, but we have to change sign, so this is 2g minus 10. And the dimension of mv is 2g minus 8. Okay, well. Okay. And so let's start with, so now, what do we have? Let's ask ourselves, what should this look like? So these are rank 2 sheaves with C1 equal whatever, and some Chern class, okay, which you can work out from, okay? And so if F is in this moduli space, the Euler characteristic of F, as I said, you sum R plus S, is 2 plus 2 equal 4. Stability, let's say, by stability and their duality, H2 of F is 0, because H2 of F is the same as H naught of F dual. You cannot have sections of F dual because C1 of F dual is minus H, so there's no section. So expect that generically H naught of F is 4, i.e. we have and F globally generated. I mean, this is a natural expectation, i.e. we have okay, and another way of saying it, i.e. we should have X. This X should have a map to the Gaussian of 2 planes in C4, and such that F is isomorphic to the pullback of the tautological whatever. Okay? Vector bundle. Okay? So you should get these F's by mapping X into the Gaussian, and of course the Gaussian of 2 planes in C4, this is by Plucker, is a quadric in P5. Plucker quadric. Okay, so then a dramatic way of trying to describe this moduli space is by mapping X into the smooth quadric in P5 and pulling back the tautological. Okay, so now if we have G equal 4, which is the first case, then we should get a 0-dimensional space. Well, in fact, as is Q prime intersected a cubic in P4, this is a 3-dimensional quadric. Okay, and then we can see that if we embed it into this Plucker quadric, we get our thing. Now, more interesting is G equal 5, X generic. It's always X generic. So then we have many quadrics containing it. And in fact, the ideal of quadrics containing it this is a P2, okay? And if we have Q prime in here smooth, well, then we have X is in Q prime. So we do get this kind of, we can pull back the tautological, only that we have essentially 2 different identifications of Q prime with the Plucker quadric. Depends whether this has 2 rulings, whether which ruling goes to which ruling here. I mean, the fact is, or another way, I mean, once you have such an F, you also have an E, and if you take the dual of E, it has the same Chern character of F. So this gives you, Q smooth gives you 2 such f, and if a q prime singular 1f, so essentially what you get is that this moduli space has a map to this thing, which is a P2, and over Q we have the Q choice of ruling, okay, and if you look at the singular quadrix here, it's a sextic curve, and so this is 2 to 1 branched over sextic. So this is a K3. Of course, so hence a K3. Okay? So you see that we get, of course, if it's a symplectic surface, I mean, this is, I'm in the generic case, this is equal to the stable. I mean, it's, okay, and that's what it is. Okay. So if you look at G equals 6, you also get a very interesting case, but I'm running out of time, so I won't do that. But I'll get back to the case G equals 4, so I'll do like Claire does, and I'll write G here in a small G equals 6. I'll get back to that. Okay? So well, maybe I'll write something. So in this case, this is 2 to 1 over a sextic curve in P5. It's not a sextic curve, a sextic hypersurface. Okay? And something similar, I mean, you have to look at rank 6 quadrix containing X and so on. And this very nice example is due to Mukai. Okay, now. Yes. It's a codimension 1 subfamily of double EPW sextics. Okay, so now what are okay, so now I want to state a general theorem, but unfortunately one would need to introduce something about polarizations, but I'll be very sketchy because we don't have much time. So now we want to state a general result about these moduli spaces. First, about the polarization. Okay? Now, so choose X. Fix V a Mukai vector. Okay? So we want to consider semi-stable sheaves with that Mukai vector. Okay? Now, there is, I'll just draw a picture. The ample cone of X tensor R, we have something like that. And what happens is that we have a locally finite subdivision. We have hyperplanes which give a locally finite subdivision of the ample cone with the property that that when the polarization is in the complement of these things, that's the moduli space is as smooth as it can be, let's say. So H in an open chamber, M as smooth as it can be. Okay, let me explain just in words. What that means is Okay, so so if it is Z, but to actually prove the results, such as what I want to say in a few seconds, you need to have pick at least 2. So you need to go through the V generic, because you want to deform X. So you cannot avoid, yeah. Yeah. So what this means is that, I'll leave it as it is. Okay, so, and this is, so let's say H, we call it V generic. What is important is that this depends on V, but once V is fixed, you have this V generic, okay? And now let me state a general result. So V generic means that you can express it in terms, it's more correct to express it in terms of semi-stability. So you have the minimal set of properly semi-stable sheaves. You really get only those which cannot be avoided if the polarization is V generic, okay? And so right. Right, that's what I'm saying. Okay, so for example, if V is, that's a good example because this is exactly in the next theorem, V is primitive. So, example regards, if V is primitive, not divisible, then MV is equal to MV stable. Of course, here H is important. It has to be V generic. Okay? But if V is not primitive, you will certainly get non-stable things. Okay? So the general result is this has many people contributed. I certainly will forget someone. And this is the final form. And also Mukai, I mean, this was the beginning, I think, of Fourier-Mukai transform. Mukai did both abelian surfaces and K3s. These were only with K3s, and this is the final form for both K3s. And okay, so now we choose V squared at least 0 for X a K3, and then 1, this moduli space, H is V generic. This is important, that's why I introduce. Then M is a hyperkähler of type K3n if X is a K3, and a certain Beauville-Bogomolov factor of M is a generalized, is a hyperkähler of Kummer type if X is an abelian surface. But 2, also, this is a very nice formula which actually I found in, Mukai gave it as one can prove, but then there was no proof. So So since we know, let's say, I'll write it here. Let me write it only for K3. Because otherwise it's not H2 of this thing, but it's of this Beauville-Bogomolov factor. But let's leave it. I mean, there's a similar one for a billion set. So this is isomorphic to V perp. So this Mukai formula tells you, I mean, what is this with the Beauville with as lattice, okay, given by the Beauville-Bogomolov quadratic form. Okay, I mean, let's say here, let's say V squared at least 2. Because if V squared is 0, you have to take this modulo multiples of Z. Okay? Now, this formula... Say it again? I can't hear. I'll come here. Yes. There is a map. There is a map. Yes, there's a map from. You see that there's a. I mean, by taking Cournot components, assume you have a universal sheaf. By taking Cournot components, you can get a map from all the cohomologies. I mean, take it to H2, but then it's well defined on the perpendicular. It's essentially Donaldson kind of map. But there's something extra. Yeah, the determinant 9 maps. Yes. Okay, but now this. So this thing is what I wanted to maybe emphasize, that you even get somehow explicit examples which go beyond just Hilbert schemes. For example, if you use this formula and you look at this moduli space, which has this somewhat explicit description, you will see this. Mukai pointed out this. I mean, although he didn't prove the formula, but you can see that, for example, if pic of x is generated by H here, you see that this 4-dimensional moduli space is not birational to Hilb 2 of a K3. You look at its periods, and you see that. So, I mean, it's... You mean that the moduli space is irreducible? I mean, for example, for K3s, I proved that essentially when the rank and the divisibility of L are co-prime. I mean, that's what I did. I wrote it as the L is primitive, but essentially if the rank and the divisibility of L are co-prime, then I get irreducibility. I mean, I get the whole thing. I mean, one has to go, at least as I did it, one has to go through Daniel's proof that birational things are, okay, deformation. One maybe can avoid that by being more precise. So anyway, the main elements in the proofs of these things are you deform the K3 among polarized K3s to get something where things are maybe easier, like an elliptic K3 with a section. And then what you do is you apply Fourier-Mukai transforms. Although I didn't formulate it that way, but essentially Marian and Oprea used my results and they showed that. So usually you have all these Fourier-Mukai transforms which give you birational maps between modular spaces with different Schoen classes, and that's how you pass from one to the other. And you also have to deform. Well, I mean, you can do directly, I mean, the way I did it, you show that you can deform it to, I mean, if you know that it's smooth and you deform it to something which is smooth and irreducible, it had to be irreducible to start from. And I deform it to something which is birational to Hilb n. Yeah, okay, so you can do zero-dimensional. There's this very nice simple argument by Mukai, and then, so non-emptiness, I mean, there are various contributors to non-emptiness, which is in general more, I mean, okay. Now, I don't want to abuse people probably want to go to lunch, but let me state what happens now if we have. So I missed out the key hypothesis here, that V is primitive. Okay. I'm sorry. So this is the key hypothesis. This V primitive and V generic gives you this equality. Okay, and then, okay. But now what happens? So now if V is divisible, now we write V as MW and W primitive. And we also, we don't want to have trivial cases, so we get V squared at bigger than 0. So now we will certainly, this so we will get, certainly, H is V generic. Although H is V generic, we cannot avoid having semi-stable, non-stable. So this is where, maybe unless some trivial cases and MV singular. No, I mean, with these hypotheses, everything is. So, and it is singular. It is singular there. So now, with these hypotheses, there is a theorem. And I'll put together various results. So, if M is 2 and V squared is 2, which means with these hypotheses that the dimension of V is 10. I'm sorry. Let me. So, since we have this situation in which we have a singular moduli space, the question is, so what we have is we have a symplectic form away from the singular locus. So the question is, does there exist a symplectic desingularization? So we want a desingularization so that the symplectic form on the open subset here extends to a symplectic form here. Okay? So in this case, a symplectic, let me write it, this exists. Okay? And no. Also of an abelian surface. It's the same. I mean, the same proof. Exactly. So this now, now I'll distinguish. X is a K3. Then this MV tilde is a hyperkähler. And B2 of this thing is 24. So I proved that it's a hyperkähler, and B2 is at least 24. And Rapagneto proved that it's equal. And he also gave the Beauville-Bogomolov quadratic form. This is the K3 part. And then we get, and the Fujiki constant with my normalization is 1, the same as for Hilbert schemes of K3s. And then if X is an abelian surface, there exists a Beauville-Bogomolov factor of mv tilde, which is a 6-dimensional hyperkähler with B2 equal 8. I proved this, but then Antonio gave the Beauville-Bogomolov quadratic form is the H2 of the abelian surface, yes, plus, okay, and the Fujiki constant, okay, with my normalization is 4, which means it's the same as for the 6-dimensional generalized Kummer, okay, and and then here there are at least, so this is partial. If m is bigger than 2, or w squared is bigger than 2, mv does not have a symplectic desingularization. And maybe the last thing is Yoshioka, but you can also see a recent thing by Perego Rapagneto. I mean, in Yoshioka, it's inside something which is essentially it's him. So we have deformation type with locally trivial deformations. So this is the main principle I wrote at the beginning of these moduli spaces. Now I'm taking the moduli space, of course, depends only on m and v squared. So if you have two different polarized K3s and you have chosen a certain m valid for both and a w on one and a w on a second one with the same square, then you can deform these moduli spaces with locally trivial deformations one into the other. So in particular, these, you only get one deformation class, and yeah. Okay, now I wanted to say one last thing, but I'm really out of time, so.